So today we're looking at polyatomic ions. First up, what are they? So polyatomic ions are a group, two or more, oftentimes more than two elements, that make up just one ion. So last week we looked at different ions. You had your metal ions, we just changed from like calcium to calcium ion, so it's pretty easy. And then with your anions, that were like, oxygen becoming oxide. Polyatomic ions, kind of like the prefixes say, if you guys are familiar with your Greek prefixes, poly means many atoms that make up an ion. So a couple of examples. NO3, -1. So we've got a nitrogen, 3 oxygens all together. That whole compound has a -1 charge. And that's what we call nitrate. That is a polyatomic ion. Or SO3, -2. 1 S, 3 O's, all together. The whole thing has a -2 charge. And we call that one sulfite. Don't worry, you don't need to know that. You don't need to memorize that. The reason why is on the back of your periodic table. There is a list. So on our cheat sheet here, there is a list of all of the common polyatomic ions we'll end up using this semester. So it takes a minute. It may take several minutes or several minutes over several problems to kind of go through and get familiar with them, but they're all right there. We just have to take the time to find them. So again, on the back of your PT, there's a list of the common polyatomic ions that we'll be using in this class. All right, when we're naming with our polyatomic ions, this whole chapter is about naming. So that's what we're taking a look at. Let's start by going formula to name. You're going to identify that you have a polyatomic ion because there are more than 2 elements. So if you guys remember last week, we looked at binary ionic compounds. And I kept harping, binary means you have just two elements. That's what binary meant, or means. Whenever you have more than two elements, boom, right there, right off the bat, you know that you're working with a polyatomic ion. So as example, CaNO3. Right there, you should see, hey, there's more than two elements. We've got Ca, we've got N, and we've got O. So we can't just follow the rules that we had for the binary ionic compounds. We've got a polyatomic ion. KMNO. More than two elements. We can't just follow those binary ionic compound rules. We've got a polyatomic ion. Luckily, most of the polyatomic ions we're going to work with are going to be anions, meaning they'll be the second half of the compound. So you don't have to look at this and be like, wait, is it CaN or NO3? Which is the polyatomic ion? You don't have to look at this and say, oh, is it KMN or just O? They're almost all anions, which means they're almost all negatively charged. So they're almost always the second half of the compound. The first half is almost always a metal, positively charged. And then that second half is your polyatomic ions. So hopefully that helps to identify them, knowing that you have more than two elements, and then it's almost always the back half of the compound. The one big exception that we're going to work with ammonium, which is NH4 plus 1. That's really the only positively charged polyatomic ion that we're going to work with. So that one we kind of have to watch out for. That one will come first. But outside of that one, they're all negative. Take a look. Everybody in this column here has a -1 charge, all negatively 1 charged anions. Everybody here, -2. These are our -3s, and then look, there's our one positively charged polyatomic ion. So the vast majority of them are negatively charged. The only one we really got to watch out for, ammonium. So because they're almost always negatively charged, we're going to start by naming the metal. So again, most of our polyatomic ions are the second half, so name the metal to begin with. Then name the polyatomic ion. Take a look at a couple of examples here. All right, again, what we're looking for, more than two elements. We have Na, we have Cr, and we have O. So we've got 3 elements there. That means at least one of them is a polyatomic ion. It's going to be the back half because it's not NH4. So that means this is just our metal. We'll start by naming him. Na is sodium. So we'll start by naming sodium. Now we need to find CrO4 on the back of our periodic table. And again, especially at the beginning, this might take a little bit of time. It's okay, be patient, it'll be there. CrO4. All right, not in this column. Ah, there it is. Chromate, CrO4, chromate, there she is, chromate. So this is sodium chromate. And there we go. We have named our polyatomic ion. Man, this is a big one. A lot of letters in this one. N, H, H, C, and O. That's a really big one. All right. So, hey, right off the bat there, we've got, here's our one exception. Here's our NH4. So that's ammonium. And then we've still got a whole bunch of letters after that. So that probably means here's another polyatomic ion, HCO3. So we have to look at the back of our periodic table at our cheat sheet, see what we have. HCO3, that's what we're looking for. Right, there it is, HCO3. There's two names for it. You're more than welcome to use either hydrogen carbonate or the more common name, bicarbonate, which you probably heard. Sodium bicarbonate, like baking soda. So ammonium bicarbonate. Fe2SO4 3. You'll notice we've got parentheses around this one. It's kind of like algebra, where the 3 applies to everything within the parentheses. So we have 3 of the entire polyatomic ion, 3 of the entire SO4. Iron. Ooh, iron's one of our transition metals. So that means it's going to have multiple oxidation states. It can either be Fe+2 or Fe+3. We're going to kind of have to reverse engineer this to figure out what he is. So SO4, let's find SO4. There it is, SO4 sulfate, and it has a -2 charge. Everything in this column is a -2 charge. And there are 3 of them. What that means is that there's a total of -6. 3 -2s is a total of -6. That must mean that I have +6 on this side. And because I have 2 irons, each iron must have a +3 charge. 2 times +3 is +6 to cancel out our -6. All right, so that means we're working with iron +3. Either iron 3 or ferric. Again, I like that you guys used both names. I think it's the best way to get familiar with some of those classic names that you do occasionally see. So, iron 3, and again, we've got to look up that. I forgot what it was. I know it has a -2 charge, though. SO4 sulfate. SO4 is sulfate. So it's either iron 3 sulfate or the classical name, ferric sulfate. Ferric sulfate. questions so far? And I'll pause for a minute here to see if you guys have any, because to move forward, got to turn the page. All right, I'm moving right along. Next, let's go name to formula. So what if I give you the name and you have to come up with the formula? Again, last time we looked for a trick, more than two elements. We're going to do the same thing. We got to start by identifying what we're working with. And the best way to do that So the best way when you're giving a name to recognize that you have a polyatomic ion is that they all pretty much end with, here, you guys can take a look even. They pretty much all end in either ate or ite, ATE or ITE. So whenever you're given a name, if you see that ATE at the end or ITE at the end, you should think, that's a polyatomic ion. I'll figure out what that is by looking at the back of my periodic table. There are a couple of exceptions, and these get kind of tricky because remember, on the front side of the periodic table, we always added the three letters IDE, like chloride or oxide. Well, unfortunately, there are three polyatomic ions that also end in ide. So we have to watch out for these three. Cn-1 is cyanide. OH-1 is hydroxide. And O2-2 is peroxide. So we got to watch out for those three. They end in IDE, so they seem like they'd be on the front of the periodic table, but we just got to kind of be familiar with them. Cyanide, hydroxide, peroxide are on the back. Those are polyatomic ions. Otherwise, best way to know that you're working with a polyatomic ion, look for ite or ate. If it ends in ite or ate, it's on the back of your periodic table. You kind of saw this a little bit on the front. We had an example or two there. Whenever you have multiple polyatomic ions, use parentheses to specify the entire ion. No parentheses if they're not needed. So if you don't have multiple polyatomic ions, don't use parentheses around them. Take a look at a couple of examples, and then I'll set you guys loose. Barium hydroxide. Hey, right off the bat, we've got one of those IDEs. There it is, hydroxide, OH -1. Let's start with barium, though. Barium on the front of the periodic table. There's a metal. Here he is, barium, +2 charge. So there's barium as the ion. Then I've got that hydroxide. Again, we've got the note of him up here. Hydroxide has a -1. We're pretty much going to treat this exactly like we did before. We're going to cross over, bring the 2 down here, bring the 1 over there. We don't have to write the 1, it's redundant. But we need 2 OHs. And then here's the thing, the way I have it written right now is I have O, 1 O, and 2 H's, OH2. I don't want 2 H's, I want 2 of the entire ion, OH. And that's why I use the parentheses. Barium hydroxide is Ba, parentheses OH, parentheses 2. So now I have 2 of the entire ion, which I need to cancel out the +2 of the barium. Calcium carbonate. Hey, there's that ATE. That's my symbol. I've got a polyatomic ion there. Kind of looks like carbon, but it is not. It is carbonate. It's the polyatomic ion. I'm going to start with the metal, calcium. Find him. There he is. +2 charge. Now we need carbonate. And again, it might take a little bit, a few tries before you guys start getting the hang of it, and that's fine. We need to find carbonate. Not in this list. Aha, there he is. CO3 with 2 negative. Again, everybody in this list is a 2 negative. So carbonate, CO3, 2 negative. Okay, we'll do our crossing over. I don't want 32 O's, so I put in parentheses. Now I've got 2 of everything in the parentheses, 2 CO3s. But here's the thing, always need to reduce whenever possible. 2 and 2 can be reduced down to 1 to 1. So really, this is CaCO3. 1 calcium, 1 carbonate. No parentheses because they're not needed. This is calcium carbonate. Copper 2 nitrate. Well, hey, I'm pretty confident I know what those Roman numerals are, but always good to double check. Copper 2 means it's copper with a +2 charge. So here's my copper 2. Nitrate, the ATE at the end lets me know I'm working on the back of the periodic table here. Need to look up nitrate. There it is. NO3, just a -1 charge. Again, cross over, bring the 2 down there, bring the 1 over here. We don't need to rewrite the 1, it's redundant. Let's write Cu. NO3, again, I don't want NO3, NO32, I want 2 NO3s. So I put the parentheses around it, the 2's on the outside. That implies I have 2 nitrates. And there's copper 2 nitrate. Last example, mercurious phosphate. Again, it looks a lot like phosphorus. Don't let that confuse you. It ends in ATE. If it were just the ion for phosphorus, it'd be phosphide, IDE. But this is phosphate, ends in ATE. It's going to be a polyatomic ion. First, mercurious. It's a mercurious one. Sounds like mercury. It is mercury. But mercury is a transition metal. So we need to find which one we're working with. We flip it over. We have mercury 1 and mercury 2. Mercurious is mercury 1. Now, again, that's our oddball. That's our diatomic ion, so Hg2 plus 2. I'll start with that. There's mercurious. Phosphate, okay, that ATE lets me know it's on the back of the periodic table. I got to find them. Not here. Not there. Aha, there he is. Way over here in the -3 column, PO4, -3. Got to get these charges to cancel out. I think a quick way to do that is crossing over. Bring the 3 down, bring the 2 down, and rewrite it. I have 3 of my Hg2, so I got to put a parentheses around Hg2, otherwise it's going to look like Hg23. And I have 2 of my phosphates. So this one has a lot of parentheses, a lot of little side numbers, 3 of my Hg2s, 2 of my PO4s. That's mercurious phosphate.